Hi, I'm Chris Moyer. I work in the STK development with the communications and radar module. I've been here at AGI for 14 years. My forte is communications and radar systems. I'm here to talk about the STK over-the-horizon HF model we incorporated with STK 12.1. It is an incorporation of VOACAP model. VOACAP is a slightly modified version of IonCap, which stands for Ionospheric Communication Analysis and Prediction. This allows the prediction of Skywave propagation effects. What is Skywave? Skywave is a signal when it enters the ionosphere. The ionosphere will bend it back down to Earth. And this provides long-distance communications or long-distance emissions, and it can be even considered global communications or global emission. The ionosphere is a very dynamic in nature. It will provide changes in signal based on frequency, based on transmission, and the entire solar effects. So it has a solar cycle dependency, which is an 11-year period. It has a seasonal effects, which is the Earth's orbit around the sun. It is also dependent on the diurnal, which is the 24-hour rotation of the Earth, and latitude, as well as hardware aspects such as transmit and receive frequencies, and transmit and receive angles. So I want to just discuss a little bit about the transmit and receive frequency and angle dependency here, because there are some very basic aspects. If we have a transmitter here on Earth and we send a signal up into the ionosphere, we have an ionosphere here. The ionosphere actually consists of multiple layers. Let's see, you can't quite see that. Let's do this here. The D layer. We have an E layer. We have an F1 layer. And we have an F2 layer. And the signal will refract differently through these different layers, and it will depend on these aspects that have been mentioned right here. So if we send, let's assume our frequency is fixed. So our frequency is some constant. And we send a signal up into the ionosphere at some angle. It'll hit the ionosphere and it'll refract back down to the Earth. Now if we, keeping that frequency the same, and we just change our angle a little higher, it's going to enter and it'll refract again, and it'll come back down at a different location. Again, a little higher of an angle, and we'll come back down to the Earth. Eventually, if we go too high, this won't refract back down, but it'll continue on through. Thus, there is the notion of some critical angle, and that critical angle is when the signal continues to go right on through the ionosphere. But what we notice is, if this was theta 1, theta 2, theta 3, each of these angles are increasing. So we see as we increase our angle, our range, we cannot extend quite as far. So let's keep that in mind and erase all this. And let's take a look now at the frequency aspect. So if we have our emitter here, and we're now going to assume our angle of transmission is a constant. So if we have our ionosphere here, let's draw something here. We've got our 4 layers. Transmit at some fixed angle and at some frequency. And if our frequency is too high, it's not going to refract back down and it'll go off into outside the ionosphere. This frequency is, we'll call a critical frequency, just like we had a critical angle. So if this critical frequency, our frequency gets too high, goes above the critical frequency, we lose all signal. So this introduces something that we're going to call a maximum usable frequency, or MUF for short. If we transmit at the same angle, but a slightly lower frequency, we're going to end up refracting back down and we'll hit Earth. This frequency is, we'll call it the maximum usable frequency. So that is the maximum frequency before we end up hitting that critical angle and we no longer receive a signal back down. We send another signal up at a slightly lower frequency and we refract back down. So we'll call this frequency 1 is the maximum usable frequency. Frequency 2 is less than frequency 1. We'll transmit another signal at the same angle, slightly lower frequency, and we come back down and we have frequency 3 being less than frequency 2. And again, if we transmit at the same angle but a lower frequency yet, we don't receive anything back down. This frequency, frequency 4, being less than frequency 3, introduces a new concept called a lowest usable frequency. And this will happen because there's too much, this lower layer is the D layer. There's a lot of absorption that takes place there. Your signal is basically being hitting a lot of the atmosphere that's in that lower layer. A lot of molecules in there, particles, they start colliding. You end up absorbing, they end up absorbing your signal. So in fact, when the MUF, the maximum usable frequency, becomes lower than the lowest usable frequency, then you're not going to get anything through no matter what frequency you're using. But the interesting thing here to take note is before we had, as we increased our angle, we decreased our range. Here, as we decrease our frequency, we decrease our range. So we're going to take a look at these concepts now in STK. And so let's go fire up STK and take a look. So we incorporated VOACAP into STK as a propagation model. So if you go into your scenario RF environment absorption, atmospheric absorption tab and go into your list of models, you're now going to see a VOACAP model here. Once that's selected, you're going to see a list of user inputs, and I'm not going to really go through what these mean. You can check that out in the STK help, but I do want to point out the sunspot number is probably the most critical one. There's a direct correlation between sunspot number and the state of the ionosphere. And that one is going to have the biggest impact on propagation loss. So if you are doing an analysis in the future, you can go onto the website. There's a website out there that tells you what the predicted sunspot numbers will be for the future. So you can grab that number, put it in there. Maybe you're doing an analysis in the past. Maybe you're trying to find out why didn't my communication link close or why didn't my radar detect. You can go to that same website, find out what the exact sunspot numbers were for that time period, and you want to enter that in there. With that in mind, what we're going to do is I'm going to quick run down a little bit of explanation of what objects I have here in my scenario. So what I did is I put down a facility in Virginia along the East Coast, and on there I have a transmitter, which is an omnidirectional transmitter, emitter we'll call it. It's running at 13 megahertz, and we can see that there's our omnidirectional antenna on there. Then I have out here in the ocean, I have a place. And along with that, I also have an area coverage right here. There's some range rings here, so we can look at it from the perspective of a communication link, or we can look at it from a radar aspect. That really isn't the important part here. The RF theory applies to both of those. It's just how you use them makes the difference between communication and radar. Radar has a little extra aspects to it, which is, it's a bidirectional, it's a forward link and a return link. There's RCS there, but STK can take care of those things for us. So what we're going to do is we're going to use this simple model to get an understanding of the ionosphere and the aspects behind it with frequency and transmit angles. And really what we're trying to do is lay down as much power as we can in a desired location. So we're going to take away a directional antenna. Even though we know we have a directional antenna, we're going to slowly build up to that. Eventually we'll add in a sensor to do mechanical steering, a phased array antenna, and we'll even put in a directional antenna on the receiver. Right now we're just using omnidirectionals in both locations. So with that in mind, what we can do is we can go over to the 2D here, and we'll take a look at the coverage. I have a global coverage defined, and that global coverage is a very simple definition. It's set up to be that our hemispherical emitter as our asset, and our grid object is going to be our receiver here on place 2 that we're going to move around. So if I turn that on and take a look at that, we can see we got a hot spot right here, and we got some cooler spots and some outages. And what we can do is animate this over the course of a day. So this is on an hourly basis, and as I animate this, we can see that our hotspot starts to get smaller, starts to shrink, and it's really only on the south of us. Not only does it shrink, but it also starts to fade away. As the day went on, we saw that it started to come back. And now we can see that our hotspot's back again, And there's no dynamics involved here. We have two places that aren't moving. We have antennas that are not moving. They're not directional. There's no sensors that are moving. Everything's static, but we can see our environment is no longer static. So you can see the spatial temporal dynamics associated with the ionosphere. What we can do now is take a look at what a real simple link would be. So let's take a look in our 3D window again here at this particular link, run an analysis here, a real quick link budget. But before I actually run the report, I do want to introduce you to a new data providers. Our data provider here is as you're familiar with the link information data provider, that gives us the link budget parameters that you can report on but there's straight line aspects to it. So, and for over the horizon HF, that straight line isn't too appropriate for us because that would send everything through the Earth. So we have another link information data provider here called Link Information VOACAP. And this will have our Skywave parameters in it. And essentially the parameters that go from transmit antenna through to the receive antenna, any reportable parameters there are going to be found in here for the Skywave aspects. So we have our transmit elevation angle, transmit azimuth, transmit gain, the receiver aspects, Skywave propagation loss, those types of things. And if we run our report now, we only need to run it over every hour since our ionospheric data is hourly and we have nothing moving. So we're just going to run it for our 24 hours at every hour. So our link budget here, we can see we have our transmit azimuth, transmit elevation. Normally this would be, if we weren't using VOACAP, all these numbers over time would be the same. There would be nothing changes because we have two facilities. Nothing's moving. But in this case, we can see that we have changes occurring over time, and that is purely from the ionosphere. We go down through here, we can see the Skywave range. This is distance, the path up to the ionosphere and back down. Free space loss is that free space loss across that path, which is up to the ionosphere and back down. Maybe one hop, maybe two hops, it could be several hops. And then we have a propagation loss, and if no other models are turned on, these two fields, the free space loss plus the propagation loss, will sum up to be the total prop loss, which is this column here. The Skywave propagation loss is those absorption losses, ground bounce losses, layer bending losses, all the different losses that are incorporated into VOACAP. And here we can see the mode. This is telling us which layer has done the refraction to receive the most power at our desired location. And then we have a little further down, we are using an omnidirectional antenna here for our receiver, but we have our received isotropic power as well as the rest of our link budget. So there's two things I've just noticed here in doing this. One here is this region of our link budget, our received power during this portion of the day just seems to tank. So let's take a look at that in a little bit more detail. And we look over here, we know we're using omnidirectional antennas, so we know we're laying down the most energy from the ideal direction. So that implies that we have the wrong frequency, or just the problem is associated with the frequency. So let's go ahead and run another report that we can do to help verify our suspicion here, and that's this my reliability. So what we have here is a graph that is over the course of the 24-hour period. On the y-axis we have my reliability, which is the reliability of my frequency. That's why I called it my reliability. It's for my frequency. Every frequency will have a potentially different reliability. But here we can see that we typically want to operate at 95% reliability, or maybe 90. But in the end here, for this first half of the day, we're not meeting decent reliability numbers here. And in the second half of our window, we look good. So we can run one more report just to find out, so we know our frequency isn't good. Let's try to find out what frequency might be available to us. And here is the maximum usable frequency. This is, again, across the course of the 24-hour period, we have frequency on the y-axis, and we know we're operating our transmitter at 13 megahertz. And we can see from this graph, we are trying to operate well above the maximum usable frequency for this first half of the day. So maybe we can ask ourselves, well, it looks like we can get away with 7 megahertz, but maybe we don't have 7 megahertz. Maybe it's being utilized, but we can use 5 megahertz. So what I did is I threw down another transmitter real quick. I copied that one, and I'll put in 5 megahertz here, and we'll just quickly run that report on 5 megahertz, the reliability report, to see what kind of reliability we can get out of 5 megahertz. And we can see the first half of the day, great. We have great reliability, but the second half of the day is not very good for 5 megahertz. So at least we have identified our frequency that we can use for the second half of the day as our preferred frequency of 13 megahertz. And for simplicity of this example, let's just say 5 megahertz isn't even an option for us. We're just going to have to deal with an outage, and we'll really concentrate on the second half of our day. So now we've identified a frequency and a frequency issue, but there was something else in that report that I noticed, and that other item was right here at 1400, 14 to 18. I can see that we have a different angle. So this is saying the maximum energy that can get laid down is if you're transmitting from roughly 9 degrees. So we're going to want to keep that in mind when it comes to directional antennas. So let's go ahead and now move forward and let's look at our directional antenna aspects. So what we're going to do is lay down a sensor. This sensor will have a fixed pointing, and we'll use our report here, which was our transmit azimuth was 133.7. We'll point our sensor in 133.7, and we'll pick 34 here for its elevation angle. That's going to be our fixed pointing for now of our sensor. And on that sensor, we're going to throw down a phased array antenna. So with that antenna, 13 megahertz and 37 elements. But we can take a look at that in the 3D window to see if we have that pointed appropriately. So we have our phased array antenna there. It's pointing in line with our place 2, and we can see we have a reflection point that's around 300 kilometers up. So with that in mind, what we can do is run a link budget with that phased array antenna emitter. And our report here shows us we are now pointing at 35, somewhere, the most power is going to get laid down anywhere from 32 to 35, 36 degrees. And we can see we have almost max gain. Max gain is around 20 dB. But the one thing we can note is we're not using the optimal angle down here in the second half of the day. And we can take a look at our mode. We are using the F2 layer, and we're not taking advantage of the E layer. And if we take a look at where that E layer was, that was at, our time period was 1400. We've got minus 74 dB of received isotropic power. So let's go ahead and change our phased array antenna, and let's have it do some electronic steering. So what we're going to do is we're just going to use a external file for this, and I can show you what that looks like really quick. It's a really simple file. We're just going to say, hey, at this moment in time, this is 1400. We're going to switch to 34 degrees minus 9 is going to be 25. So this 25 will put us at 9 degrees. Otherwise, we're going to be continuing just to point at the mechanical steered direction. So with that in mind, we're going to select that, refresh this report, and now we can see, oh, great, we are now making use of the optimal direction, which will lay down as much energy as possible. In fact, we've got, our main transmit gain is still the same, but now we're sending it out at a more optimal angle. And we can see here we're making use of the E layer, and we have minus 68 dB of RIP. So we've gained about 6 dB. So we've been able to optimize our system a little bit more. Worth showing you at this point in time is let's take a jump over here to the 3D window, and we'll take a little look at our area coverage now. So if we turn on the area coverage, this is with the phased array antenna, of course, of our area of interest. A couple interesting aspects here we can see is the phased array is putting down a good amount of the energy where we need it to be in the place 2. We also see another hotspot back here, and that's the second hop that's taking place. But what we can do here is animate this just to see how things progress throughout the day, looking more focused on our particular area of interest. And again, we can see as the day moves on, we really lose our hotspot. At 1400, you should be able to see the phased array antenna change positions. And we actually incorporate our place into that new contour. Otherwise, it would have fallen down into a lower contour. And finally, as the day finishes up, our power laydown starts increasing again. So I've been able to kind of show how you can go from a very simple scenario and build it up into something a little bit more elaborate, as well as kind of help understand the frequency and angle aspects associated with the ionosphere. One last thing I want to just quickly show is how there's one more data provider that we introduced, and that is for those that are familiar with VOACAP or IonCap. If you go into our report data providers, and I'll just take a look at this one. There's another data provider called VOACAP Files, and there's another one for radar, a similar one for radar. If you're familiar with VOACAP or IonCap, it's a command-line executable that takes files as input data and will produce an output file. So here we have an input file, which is the system parameters, transmit antenna input file, receive antenna input file, and an output file. So if we actually run that, I'll run all of them, and you have to pick a time. It'll report it out at one moment in time. You don't have to save the files to the scenario directory, but in this case I'm going to for you. Here is the VOACAP system input file. Here is the transmit antenna input file. Here's the receive antenna input file. And here is the VOACAP output file associated with that. So this concludes hopefully what is a little tutorial or 101 on the HF model now in STK and how to use that to understand what is occurring. Contact info@agi.com to learn more about our new feature. Thank you.